Okay, I think we can start. Welcome everyone to the afternoon session, and it's a great pleasure to introduce Stefan Woerner, Dr. Stefan Woerner, which is a principal research staff member and the manager of quantum application research and software at IBM Zurich, IBM Quantum in IBM Zurich. And he obtained his PhD at ETH Zurich in applied mathematics. And yeah, again, it's a pleasure to have you. The floor is yours. You have more or less 1 hour and 45 minutes.
Thank you for the introduction, for inviting me to speak here today. So welcome everybody. I'd like to give you an overview of quantum optimization or quantum algorithms for optimization and some recent results, some projects we worked on, and where I see this might be heading and where I think there might be some possibilities in the nearer future for potential quantum advantage here. So very briefly, there are different ways to look into application and into optimization and different optimization problem classes. This is maybe not exhaustive, but I want to give some kind of classification. So here we have continuous and discrete problems and mixed continuous and discrete problems. And we have convex problems, non-convex, and black box problems. Black box usually means we don't have access to gradients. Now, I added some examples for this, like in convex we have linear programming, semi-definite programming for convex continuous, convex non-continuous, convex discrete. We have then also the linear and quadratic programming with integer or binary variables. And we have kind of the mixed versions. If you go to non-convex optimization, there are neural networks. There's polynomial optimization in the discrete case, or for example, mixed integer non-linear programming. And all of these find plenty of applications. So these are quite important application classes. In black box optimization, there's things like simulation-based optimization. If you have a complex system, you simulate that and you want to optimize some parameters. In discrete black box, there's something like optimal feature selection. I'll get back to that later. Where suppose you have a data set, you select some features, you train a machine learning model, you score it, and this is the optimization problem. And mixed integer programming for black box, I mean, there's also like optimal control, optimal design problems where you try to control a complex system. So these are different classes. In general, most of them are very difficult. Like this one is solvable in polynomial time classically. The rest is in general NP hard or worse. Black box systems, it's a little bit, it depends very much on the black box. But this is like the map of optimization problems. What I want to focus on in the next 1 hour, 1.5 hours is briefly on the continuous part and then a bit more deeper on the discrete optimization part. There are also some results for mixed integer optimization already in the quantum computing setting, but mostly the quantum advantage in these cases is expected to come from sub-primitives that look into this part. All right, so let's briefly talk about continuous optimization. So there is a bunch of literature. There are some proposals for training neural networks, speeding up gradient evaluation, and also semi-definite programming. All of them have usually some kind of problem. This is, I think, true for most of the proposals in continuous optimization on a quantum computer. Either they assume some QRAM or some black box that gives you the input in a quantum form. And this is usually a problem because that black box can be extremely expensive, actually more expensive than like solving the problem classically. So this is kind of a bottleneck for these classical optimization problems. And the other part is that often there is a speed up. The speed up can be quite huge in the problem size, but then this introduces an often exponential dependency in some other problem property, like some condition number of a matrix. And then you're trading off one thing against another thing, and this usually cannot be applied to practical things. So there's always some kind of catch if you look into the literature today for quantum optimization for continuous problems. So to conclude on this field here, I really just wanted to give a very brief summary. Quantum optimization for continuous problems is very interesting because it has the potential to really achieve super quadratic speedups, really like polynomial speedups of higher orders. which can be quite cool. But it always comes with, or at least today, always comes with some catch, and we don't really know of a practical algorithm. Let's assume fault tolerance, that's not a problem, but a practical algorithm that end-to-end for a practical problem would really promise a speed up. So with this, and I said it likely requires fault tolerance. The reason is that the classical algorithms are pretty good. Like we can scale to relatively large problems in continuous optimization. So you need a problem size that's relatively large before you can do something interesting, which usually translates to a lot of qubits or very deep circuits. And that means that likely we have to use error correction to deal with the noise in the system. So this is a very brief summary of the literature in continuous optimization. It's by no means exclusive, exhaustive, but it gives an idea about what the problems there are. So I think it's very interesting. It definitely makes sense to further pursue that, but from today's point of view, we don't have really a good understanding of how to apply this to something practically relevant. All right, now discrete optimization. We have also these three things: convex, non-convex, and black box. Okay, we had. So for convex, it's like, again, linear integer programming or linear binary programming or quadratic integer binary programming. For non-convex, it's the same. Here I have one example. If you just have this quadratic form, if Q is positive semi-definite, then this is a convex problem. If it's not, then it's a non-convex problem. For black box optimization, I already mentioned that. You just have a function that you can evaluate, and let's suppose we have some binary input, and you have this input, you get a function value. That's all you know about your problem. Then the question is, what can you do? All right, so this is, you probably have heard about this, a quadratic unconstrained binary optimization problem, or QBO. This is what we'll focus on for the biggest part of that talk today. It's a very interesting problem class. It's still very difficult. You can model many things with that. Just gave 3 examples here, like portfolio optimization or some routing problems. Also, optimal feature selection can be cast into this form. Okay, so this QBO problem in this binary optimization form is one way to represent it, but often we want to map it to an Ising Hamiltonian. And I just want to briefly go through the steps how this is done. So you see here the QBO. Now what we can do is we replace the binary variables by binary variables that take values plus minus 1 instead. That's really just this affine transformation. And you end up with a new problem that looks a little bit more complex because this introduces linear terms and also this offset, but it's essentially the same. Then what we do is we take this plus minus 1 binary variables and we replace it by Pauli Z matrices. And now the eigenvalues of this matrix correspond to the values of the variables. If we have a quadratic term, then we replace it by this tensor product. Now what happens is that the eigenvalues of this Hamiltonian correspond to all the exponential number of possible solutions to this problem, or possible inputs. So what we did is we translated the original problem, which was a binary optimization problem, to a ground state problem of this new Hamiltonian. I made here a small example, and I will use this example to illustrate some of the other techniques. So here I chose a particular Q matrix. If you would solve this problem, you find this as the optimal solution, which gives you just this -2 here. If you translate this to an Ising Hamiltonian, you get to this. Here you see the different terms in Z, Pauli Z matrices, but it just constructs in a very compact form this diagonal matrix. And then this would be the basis state with the ground state, which gives you the -2 again. We switch between those two representations as needed. All right. In most of the remainder of the presentations, I want to discuss a couple of algorithmic primitives that we use in quantum optimization to build quantum optimization algorithms for discrete problems. And you've probably heard about some of them before. The first one is Grover search, which can be seen as a candidate of quantum walks, which might be a bit a larger class. The second is adiabatic annealing. And the third is imaginary time evolution. All right, so I'd like to use this example of Grover also to address one of these common misconceptions that you probably have heard and probably know that it doesn't make sense. question is, can quantum computers evaluate all possible solutions at the same time? That's what you read in the media all the time. And let's look at this example. Suppose we prepare an equal superposition state, so all possible basis states in superposition. And suppose we have such an operator that takes these 2 qubit registers, x0, and maps it to f of x for some function. Now, if we apply f to this equal superposition state, then we actually get to this. And then, to some extent, the quantum computer evaluated all options in parallel. So far, so good. The problem is that it's still an exponential number of options, so it doesn't tell you which one is the best. It just has all in superposition. We don't have access to that. And if we want to measure the optimal or good solution with a probability larger than just this 1 over 2 to the n, then we have to work a bit harder. And I mean, this is what the other 3 algorithmic primitives are about, to try to get a higher probability to good values. Very briefly on Grover search. Suppose now we have such a function f that takes either an n-bit string or an integer from this set and maps it to 0, 1. And we have an oracle u of f that flags a bit string or an input state by multiplying it by -1 if f of x is equal to 1. So it's kind of, it flags all the states with a negative amplitude if f maps to a 1. Then Grover search can help you to find a state that leads to a 1 here, or -1 here, with square root of 2 to the n oracle calls, while classically the best you can do is 2 to the n oracle calls. And I mean, you've probably seen this. You start in equal superposition. You mark the item of interest by your oracle. You do a reflection around the mean, which helps you to amplify the probability you're interested in, and then you repeat that. This is Grover search. Now, one way to use that for optimization is Grover adaptive search. It's pretty similar. So now we assume we have a function f that takes the same input, but maps it, let's say, to the integers. Could also be real numbers. And the oracle is now slightly different. It flags an item with a negative amplitude if f of x is less than f of x prime, where x prime is some state that we picked. For example, at the beginning, we just picked that randomly. And then what you do is you run Grover search to find an x such that f of x is less than f of x prime. And then you just replace x prime with x. So it's the new best solution you found, and you repeat Grover search to find a better solution. And you just repeat that until you can't find anything. In a way, it's similar a bit to binary search. In a way, on average, you reduce the remainder of your solutions by half. And so it adds a logarithmic number of iterations on top of Grover search, and then you get to the optimal solution with a high probability.
One question.
Yeah.
So you said it's logarithmic. So it's an logarithmic overhead over Grover.
Yeah.
Do you have an intuitive picture of why?
Because Grover search samples uniformly from all solutions that are better. And then on average, you kind of end in the half, and logarithmic is like logarithmic in the exponential search space, so it's in the number of qubits, essentially linear.
Yeah, sorry, what's the optimization goal here? Because you said a better solution, but if you already find one solution, so what is the goal?
That's a good point, to minimize f. So you want to find the input x that minimizes f. And so you improve and improve. Yeah. This is true. There should be somewhere a minimization problem. That's like. All right. So this is Grover adaptive search. So it's really just adding this adaptive loop on top of Grover to bring it into an essentially from a decision problem to an optimization problem. Now, to summarize this, Grover adaptive search is nice, except for this logarithmic overhead. It gives you the quadratic speedup. We know for QBOs, for example, how these oracles can be constructed efficiently. And that's on the positive side. On the negative side, the circuits become very long because you have to run the Grover oracles like square root of n times at the maximum. And that is still exponential, right? It's a quadratic speedup for an exponential problem. So it very likely will require fault-tolerant quantum computers. And the problem here is a fault-tolerant quantum computer runs significantly slower than a classical computer due to the overhead of error correction. So the operations, even though it's less, take longer. And the tipping point where kind of the quantum algorithm starts to outperform the classical algorithm will only happen at very large problems due to this constant overhead of the slower operations. And so for quadratic speedup to really materialize on like using Grover search for binary optimization, I think it will require relatively large fault-tolerant quantum computers. So it's, yeah.
Have you an idea of some numbers of like what that would, like how many logical qubits you would need at what speed?
In this paper here, you can, like it's very easy to write down how many qubits you need. Qubits, I think, is even maybe twice the number of variables. I think it's 2n. And the depth is also linear. Then you can do the math. There's also a paper by Google where they analyzed the quadratic speedups that they looked at it a little bit more general. They come to this conclusion as well. There you can look into that. You need to make a couple of assumptions, and you need to look into essentially how many T gates you get. So it's a little bit tedious to work out the details for that, but it's not very difficult. But we didn't do it in detail. All right. So much about Grover adaptive search. I think it's very interesting from a theoretical point of view, but it will take quite a while until this has any practical implications. Okay. Now, the next one is adiabatic annealing. And I'd like to start briefly with the adiabatic theorem, and I'd like to read that to you quickly. So the adiabatic theorem says that a physical system remains in its instantaneous eigenstate if a given perturbation is acting on it slowly enough and if there's a gap between the eigenvalue and the rest of the Hamiltonian spectrum. It's quite a dense theorem, but I want to look a little bit into what that means and what that means in terms of optimization algorithms. So suppose we have a given Hamiltonian like we had before. We construct a Hamiltonian that encodes a QUBO. And now we're looking for another mixer Hamiltonian that is very easy and that has a known eigenstate that's easy to prepare. And this ground state. And this ground state needs to have an overlap with the optimal solution of your problem. And what you do then is you drive your system from this ground state of your mixer slowly using the dynamics that is defined here, slowly to the ground state of your problem. And so the Hamiltonian that you apply here is time dependent, and it starts in the mixer, and then as t evolves from 0 to large T, it actually ends up at your problem Hamiltonian. And the most common choice for the mixer is this. So you just have a sum of sigma z matrices, and the ground state of this is just the equal superposition state. And by definition, this has overlap with all possible combination basis states, so this satisfies the requirements. And this is just an illustration of this mixer matrix for our problem with 3 variables, which is 8 by 8, and these are just all -1 terms that you see here. If we apply this, if we solve this differential equation for the problem I started with, you start at the equal superposition state, you anneal, and you end up at the optimal solution at -2. So this is working nicely. What I did here is I first solved the ODE, but then in every time step I also computed the ground state of the intermediate Hamiltonian, HT, and you see this nicely matches. So you always stay in the ground state, and that's nice. Now, I also plotted the spectral gap here. So this is the gap from the ground state to the second excited state, or to the eigenvalue, second eigenvalue. And this also is reasonably large all the time, so we should be all good. But in general, if we scale problems, this is exactly the problem. Because the larger we make this, the smaller this gap usually gets. And the problem is it gets exponentially small. And if you remember what the adiabatic theorem said, is if there is a gap between the eigenvalues. And if this gap becomes very small, then we need to anneal very, very slowly. The smaller this gap, the slower we have to anneal, the longer the runtime to get to actually the ground state. And this can actually lead to exponential runtimes. And if you look at the annealing papers, that's also usually the scaling you see. And this is a bit, this is the catch of this approach. Now, there we assume that we can apply this Hamiltonian directly to the system. Now let's talk about how can we implement this on a gate-based quantum computer. And what you do for that is you apply trotterized annealing. So first thing we do is we discretize time. So we do discrete time steps delta t. And for every of this delta t, we apply this, this time evolution operator here for a constant Hamiltonian. Now, since the Hamiltonian consists of two parts, the problem part and the mixer part, and they do not commute, we also have to trotterize because we cannot implement this operator directly. So what you see here is we apply a part for the problem Hamiltonian with a smaller time step, for the mixer Hamiltonian with a smaller time step, and we iterate between the two, repeat the two. And so if you have here psi t, we do m trotter steps of that part to approximate this operation. We get to psi t plus delta t. For the problem we looked at, for a single trotter step, this is the circuit you would get. So the single or the linear terms are just RC rotations. The quadratic terms are ZZ rotations, and the mixer term are just single qubit X rotations. And then you have to repeat this many times, and if you have long annealing times, this leads to incredibly long circuits. This is not really applicable because you quickly accumulate too much noise and you don't get reasonable results. All right, now, okay, that's what I said already, yeah. So it leads to very, very long circuits. Now, how can you work around that? One very common approach is so-called quantum approximate optimization algorithm, or QAOA. And what the idea here is that you build the same circuit, but you truncate it after p layers. P, for the time being, p is just a random number, and that's when we stop. Then we don't choose these angles here of these rotations based on the annealing schedule, but we actually let a classical optimizer choose them. That's what you see here. So you now have a parameterized circuit, and you just choose these parameters to minimize the energy. And this psi gamma beta is defined like this. So you see it's exactly the same structure as before. We have these rotations from the problem Hamiltonian and from the mixer Hamiltonian, but instead of choosing this depending on delta t and so on, we just optimize over them. And I think from what I heard in the break, you already heard something about the VQE, variational quantum eigensolver. This is just a special case of VQE, but where we construct the ansatz from the problem. And it's motivated by adiabatic, but since we just truncate, it is a heuristic algorithm. All right, there's one interesting paper that was in the last bullet. If you can use these angles from adiabatic annealing as initial values for the optimization of QAOA, that can help actually, and it's usually a quite good starting point. Okay. Now, how does this heuristic scale? There are a bunch of questions that one can ask to understand how performant this is, or what does your hardware need to satisfy to actually get something meaningful out of that. And we don't have sufficient conditions that guarantee a quantum advantage, but we have some kind of necessary conditions that tell us, okay, if that's not satisfied, then the chance of a quantum advantage is pretty low. And questions I would like to focus on now is first how to choose the p parameter, how many layers you need to do. Then the second one is what is the resulting number of gates, or the depth of the circuit. And that translates directly into the runtime. How fast is this algorithm? What can you actually expect? And last, what are the requirements on the gate fidelities? Because we have noisy hardware, this is supposed to be an algorithm that runs on the hardware that we have in the next couple of years before error correction. So if we think about this P and the number of gates and the circuit depth, what requirements imposes this on the gate fidelities? That gives us an idea about when this algorithm might be applicable and what kind of advantages we might be able to realize with that then at some point. And we analyzed this in quite some detail in this paper here, where you can find the details that I likely will not all show here. All right, let's focus on the first question, how to choose P. Here I'd like to first quickly point to another paper by a colleague of ours, by Sergei Pravi and collaborators. And this is a sentence from the abstract where they say a surprising consequence of their result is that the Gurman-Williams algorithm outperforms QAOA for certain instances of max-cut at any constant level. And by level, they mean P of QAOA. What this means is if you have a fixed depth of your QAOA algorithm and make that not dependent on the size of the problem, then you have no chance to really achieve a quantum advantage, because if you make the problem large enough, the classical algorithm, Gurman-Williamson is a classical approximation for max-cut, will outperform it. So what does this imply? Constant depth is not enough. You usually have to choose it, let's say, at least logarithmically. So you have to increase the depth, otherwise you likely will be able to get a better result using classical algorithm. There is a way to overcome this by a variant called recursive QAOA, and it's also introduced here, but I want to skip that for now. I will come back to that later on. So this is not a sufficient condition for a quantum advantage, but it's kind of necessary. If you don't increase the depth, then just running plain QAOA might, for at least for these max-cut problems, not be enough. Okay, the second question is, how does the number of gates and the circuit depth scale? Here we need to consider the limited connectivity of the hardware. This is very, very important because that adds quite some overhead. And this is illustrated here. Let's suppose this is our QAOA circuit, which only focuses on the 2-qubit gates and skips all the single-qubit gates, and this is for one layer. And if we assume we have a linear connectivity, so we can only entangle nearest neighbors, then we need to apply some swap strategy to implement that. And a very, very good way for QAOA is to insert these swap layers. You see here they are always alternating layers. And then you just apply all gates that you can. The important part that you need to consider here is that all gates, all 2-qubit gates, commute. So you can apply whichever of them you want first. So if we do this, first we can apply this, second one, and this one, because they are already they are native to the hardware connectivity. Then we swap these gates. Then we can apply this one. We swap these qubits, and so on. But these swap gates, they really need to be considered because they blow up the depth. A nice thing is that the swap gate and the Z0 rotation, they have some neighboring C0 gates and they cancel out. So this you can use to reduce the depth of these operations here. All right, now what does this mean for the scaling? And here we did some analysis. The swap layers that I had on the slide before, so you do a layer of swaps, and then the alternating layer of swaps, and so on. That is actually for linear connectivity provably optimal. If you want to have if you have a dense problem where you want to have an all-to-all connectivity, then that's the best you can do. And what we did is we extended this strategy to 2D grids and 3D grids, and also to heavy hex. Heavy hex graphs is what our hardware has. So it's kind of a hexagon lattice where on every edge you have one other qubit in the middle. And what we analyzed is how many of these swap layers do you need, depending on the density of your problem. We tried to provide some lower bound here, and this is what you see in this table. And so this tells you how many of these C0 layers, or swap layers you need. And what is very interesting to see is that for a dense problem, the linear connectivity is actually as good in a way as the grid, as a 2D grid. So because you can cancel so many C0s by applying these rotations and the swaps together, you don't get an advantage by having the additional connectivity of a 2D grid for dense problems. For sparse problems, that's a very complex optimization problem, but you can get better, but for dense problems you can't. If you go from 2D to 3D grids, then it starts to turn, then really the additional connectivity for dense problems starts to make a difference. We looked into this here. You see here for different problem sizes, the different number of C0 gates for different densities of the problem. Density means like how many 2-qubit variables have a non-zero entry in the Q matrix. Different strategies, where the best one is usually here the swap layers that we constructed for QAOA. And then here you see how this translates into depth. And I think the interesting part here is to see it scales linearly, which is not really surprising, but we need to understand the slope, because this then really tells us how many gates do you have to run sequentially, and that we then can translate into runtime. This is what we did then here. So this tells us, and I go through these assumptions in a second, this tells us for a certain problem size, how long do we expect QA to run. And so the assumptions are first, the number of iterations of our optimizer, or like how long does the optimizer take. And from some empirical tests, we tested different instances, it looked like 25 times the number of layers. The number of layers indicates the number of parameters in our problem. Seems a good proxy. So this is 25 times logarithm of the problem size. Then how many shots do you do per evaluation? Here we tried different things. For the instances we tested, it looked like it actually you need more and more shots with the problem size. That depends a bit on the problem, but we use this proxy as one choice, but also just like 10 to the 4 shots as a constant benchmark. But this is something that needs to be empirically studied on larger problems. And then we made some assumption about how long one CNOT gate actually takes. The best demonstrated one in literature we could find is around 30 nanoseconds. Our current hardware is more around 400. And then we added all this together, and you get to these numbers. So problem size is here, and then the resulting runtime, where you see here for 1 minute, 1 hour, 1 day, 1 year, this log scale. And in blue, we assume the 400 nanoseconds for the CNOT, and the solid line is 10 to the 4 shots. The dashed line is this quadratically increasing number of shots. And then you see here, for example, let's be optimistic, let's assume 30 nanoseconds, 10 to the 4 shots. Then here, this is around 500 variables. We'll end up with a runtime of 1 hour. So if somebody thinks about using that for high-frequency trading in finance, and you read some articles in the press, that clearly won't work. Like you might get a good solution, but you have to work for that for a while. If we really have to increase the number of shots with the problem size, then you quickly end up here with days to years. So then it's likely not really a practical algorithm anymore. But this is kind of the range. We have one other line here, the green dash dotted line. This is if you just skip the optimization completely and you just assume QAOA is giving you good quality samples, many of them, and you want to use them in some local search and some other post-processing, then this is more in the minutes. But this gives you already an idea about what to expect from these algorithms and what not. And the runtimes can become substantial even if we assume very, very fast gates. All right. Now, the last question was the requirements on the gate fidelities. And of course, if the fidelities are low, then this accumulates a lot of noise, and then you really limit the depth that you can run, the density of your problem. So then this imposes a lot of constraints. And this is now quite technical here, but this is based on this paper by Franca et al., where they showed a quite nice result, and I want to walk you through this implication. So suppose we have a certain number of CNOT gates per layer in our QAOA, and we do P layers. If this number is above this threshold, and I explain this in a second, then what this means is that there is a Gibbs state that you can classically sample from that achieves epsilon close energy compared to the QAOA state. So what this means is that if this threshold is, like if this number is above this threshold, you accumulated too much noise, so much noise, that you can actually do the same classically. There is no quantum advantage. Now what is this threshold? It has this epsilon here. This is how close you actually want to get to the noisy QAOA state. And in the denominator, it has the 1 minus the fidelity of one CNOT layer. So it's bringing together how close do you want to get, what's the fidelity of your gates, and it tells you how much or what's the depth that you actually can afford before you can do it classically. We translated this now into a concrete example. This is for 485 qubits or binary variables. We choose this weird number because for the heavy hex graph and for the grid, we can find topologies where this is pretty close. So we wanted to compare different topologies, and this was a number where that nicely matched. So for a problem of this size, if this is the density, so 1 means that the cost matrix in our QUBO is completely dense. 0 means it's all 0. So if this is the density, and if this is the fidelity of a single C0 gate. So here, 10 to the minus 3, this is probably where we are today, roughly, down to 10 to the minus 6, which is probably not too realistic. Then this is what we can, or this is the required C0 fidelity to run depth 1 QAOA on that size when we want 10% accuracy. Like if the fidelity is worse than that, then we can do it classically. So the fidelity needs to be below that barrier, the C0 fidelity, otherwise there's no chance. You can just sample from this noisy state classically. If you want depth 2 QAOA, the requirements are getting stronger, of course, depth 3. And so for running depth 2 or depth 3, I mean, we're getting already into the regime of the fault-tolerant error rates. So we're getting into, it's unlikely that you get to these error rates and that you run QAOA here, because the imposed requirements of plain QAOA are very strong. All right. Now, I already mentioned one variant, this recursive QAOA before, but I want to now spend a little time on discussing in total 3 variants or changes that you can apply to QAOA that improve the performance a little bit. The first is a CVAR objective. This is a pretty straightforward change. Usually in quantum computing, we look at expectation values. So you just average over all your samples. And if we talk about an energy, as in quantum chemistry and so on, this makes perfect sense. This is how it's defined. Since this is a classical optimization problem, our Hamiltonian is diagonal, every computational basis state is an eigenstate. So every single shot, if it's better than what we've seen before, that's all we want. So we don't need to average at all in principle. We could just always take the best shot. The problem is, if you sample 1,000 times and you take the best shot and you use this as an objective, this is an extremely noisy objective because it can have lots of fluctuations due to this taking the minimum over a set. So what we propose here is we don't take all samples, we don't take just the minimum, we take the best like 10% and average only those. This is introducing a bias to the good samples, but averaging out to remove some of the noise. And this is what's called in risk analysis the conditional value at risk, the CVAR. So if you have some samples, you just take the best 10% and you average over this tail. And if you change the objective function accordingly and you run QAOA in exactly the same way, that can help significantly to improve the performance. And in our tests, it actually also, we still cannot really explain why, but it seemed to have some kind of noise mitigating effect. Because if you have some sample which was affected by a lot of noise where you're really unlucky, you have a high chance to drop it. So this is like a little bit of intuition behind. So this seems to be a very straightforward change for VQE or QAOA for problems with a diagonal Hamiltonian. Otherwise, it doesn't make sense. Yeah, we're minimizing. We prepare this state, and from this state, energy. Now, since this Hamiltonian is diagonal, you don't need to average. Every bit string is an eigenvalue, and you can just evaluate it. And that's how we rank all the bit strings that we sample. And then we can take the bit strings that values. to this example. Here, every sample gives you these. Right. Yeah.
So you know the Hamiltonian, and you have to write explicitly.
No. You have the Hamiltonian as a sum of the Pauli strings, and from there you can evaluate it. And classically, since you started with this Q matrix, you can even just evaluate the quadratic form. So you never have to go to this exponential space. I just use it for illustration. Like if I give you a bit string, just evaluate this. Because there's a one-to-one relation between this, right? You can evaluate it on that level. You can evaluate it on this level. This is both efficient. But of course, this would be enumerating all solutions, and that's not efficient. But you don't have to. You can just plug it in here. All right, let me get back. All right. That's about the deceiver. It's a small change, but in our simulation and hardware experiments, it had a huge impact. Now, the other one is the recursive QAOA. Now, so far in QAOA, we run the algorithm, we sample from the qubits, and we take the full bit strings. And recursive QAOA kind of breaks this assumption. And this is to address this point that I mentioned earlier, that at constant depth, classical algorithms can outperform QAOA. So what is the idea? You run QAOA, you look at your samples, and you don't look at the full bit string, but let's say we only took at two variables. And what we do is we look at all our samples and we check the correlation for these two variables. Are they, since we have plus minus one, are both of them always pointing up, both of them always pointing down, or are they completely uncorrelated? If we find a very strong correlation, then it might be a good idea to just set them to one variable and treat them as a single one. So take one variable out of the problem. And that's essentially the idea. So we look at these pairwise correlators, which essentially means just we check all variables, and then we elect that has to. So if we have a pair that's always up, or always down, or always like pointing in the opposite direction, then we just replace one variable by the plus minus the other and take it out. So we reduce the problem size by 1. Then we just start again. We have now a problem that has a size n minus 1. We run QAOA. We do the same. So we eliminate one variable after the other by this scheme until we reach a certain threshold that we can handle classically, for example. And this is the whole idea. And it has been shown in this paper that for these random 3 regular graphs, this is for 100 variables, on QAOA. So recursive QAOA at depth 1 and 2, since you never look at the full bit string but only at these local observables, can actually be simulated classically efficiently. That's why they can test this for n equals to 100. So it has been shown that for this type of problem, QAOA at depth 1 achieves only approximation ratio of 50%. So we reach like half of the optimal solution usually, while recursive QAOA gets pretty high and even optimal. So you see this can make a huge difference, adding this recursive scheme. And if you then have recursive QAOA at a higher depth that you cannot simulate classically anymore, that's a very interesting to achieve a quantum advantage. All right. Now, another variant is warm starting quantum optimization. So what we do here is we take our optimization problem and we apply a solver of our choice to find good solution candidates. Can be one or multiple. And then we build a variant of QAOA that doesn't start an equal superposition state, but we bias that state to these good candidates. And then we run QAOA. It requires changing the initial state and the mixer, but otherwise it's the same. So we are starting not like all solutions have the same probability, but we already push the system to something we believe is already going in the right direction. And it's illustrated here. We start with our problem. We can, for example, relax it from a binary problem to a continuous problem that you can solve easily, but then you get a continuous solution. It's not a 0-1 solution anymore, but we can represent these continuous values by superposition states. So we prepare a state that's like if this is 0.25, that's very closer to the 0 state than to the 1 state, for example. And if you do this for each qubit state, that still has some overlap with all states, but it is biased towards a good solution. And this works for this naive continuous relaxation, but you can also work with things like Gurman-Williamson, like more advanced SDP-based relaxations and so on. And what we did is we actually now combined this warm starting with this recursive QAOA, so not exclusive, you can bring all of this together, and we applied it to a max-cut problem. So these are 4 families of problems. The left have 20 nodes, the right have 30 nodes. The top is on graphs where we randomly picked edges with a 50% probability, so an edge or not, and then with a weight of ±1. And the lower ones are dense graphs where we randomly pick the node, the edge weight between ±10. So these are very, very difficult instances of max cut. And we compared different types of algorithms. First, we compared the Gurman-Williamson, where we ran a couple of samples and took the best one. Then standard recursive QAOA, warm-started recursive QAOA, and then recursive classical Gurman-Williamson. So we applied this recursive scheme also to a classical sampling algorithm. It's the same idea, but without QAOA. And what the x-axis here is the quality of the sampled solutions. So 100% is optimum, and colors are the different algorithms. And in particular, these gray boxes here are very interesting. So what you see is that the warm-started recursive QAOA always performed the best here, and with a very high probability, it really reached the global optimum to this problem. And this is a very promising result. I mean, it's adding some logic around, so the runtimes will go up. That's something one has to keep in mind. But with these kind of techniques, we hopefully can improve the performance of these optimization algorithms while also running QAOA at hopefully a lower depth. So these are techniques that might help us to bring the requirements down to get some good solutions from a quantum optimization algorithm. All right. Now I want to very briefly talk about the Qiskit runtime. Peter already mentioned that before. Qiskit runtime is a way to run your full quantum algorithm in the cloud, close to the quantum computer. You don't have to queue for every circuit, but you queue for the whole program, and then it's executed quickly. And for this Qiskit runtime, we built a QAOA runtime program. And this QAOA runtime includes all these swap strategies. It includes some pulse-efficient transpilation that some people here in the audience developed. It allows the CVAR optimization, and you can also use this then in the warm starting, in a recursive. Like you can use that with all these techniques. Some of the things have to run on the client side, but the actual QAOA training loop, the optimization, then runs in the QAOA runtime. And we tested this on a 27-qubit example, where you see here the connectivity of the chip. Depth 1 QAOA, where we used the problem that had a hardware-native connectivity. So all the 2-qubit gates that we need to apply were already natively supported by the hardware. That led to 56 C0 gates with a depth of 6, and then we see a decent convergence. And you see here the cut value. So this is the quality of the solution. You see the results if you sample just randomly, which you can do classically. And you see the results from depth 1 QAOA in blue, which clearly improves. And depth 2 QAOA in red, which you see has too much noise. It doesn't converge anymore. We actually do the same as a random sampling. A few more numbers here. Random sampling. So the best solution that we found here with depth 1 QAOA is 10. But the optimal solution would have been 12. And the probability of sampling a solution of 10 or better, if you just do sampling, is given by 1.7 to the times 10 to the minus 6. The probability that we get here from this quantum state is 3.3 times 10 to the minus 3. So we see a significant improvement in these probabilities. So we don't get the optimum yet, but that is already pretty nice. And if we now apply this fidelity bound, if we again want a 10% accurate sampling, then 13 C0 layers should have been feasible as well. And here we have 6, and at depth 2 we have we would have 12. So 12 is just below this bound, but this bound, this fidelity criterion, is a little bit an optimistic bound because it does not consider all types of error sources. So things like crosstalk are not going into that, and so it kind of makes sense that something which is a little bit below this threshold does not work anymore. But it's kind of nicely confirming that this is not completely like out of range. All right. The last part now is mainly on imaginary time evolution. Looking at the time, maybe it would be good to make a quick break right now. 5 minutes. 5 minutes, yeah.
Okay, we make a 5 minutes break.
I don't know why this morning it was the audio problem, so I had to fix it. Just lose the signal, maybe.
Okay.
cables. I don't know. Maybe it would, but
Yeah. Okay. Shall we continue?
yes. For now, it's not jumping anymore. Sorry for that. But who knows? No, it's fine.
All right, let's move on. So the third algorithmic primitive I want to talk about is imaginary time evolution, and the idea here is that, I mean, this would be real time evolution of the problem Hamiltonian, and if you now replace the time by this imaginary time, then you get to this operator. And since we want a quantum state, we enforce normalization, so we just divide by the norm. Now, what this is doing is, if you think about it, the eigenvalues, the small eigenvalues here decay slowly, and the large eigenvalues decay very quickly. And since we normalize, what we do is we emphasize the small eigenvalues. Like we push all the weight to the small eigenvalues, to the eigenstate. The eigen to the smallest eigenvalue, to the optimal. And you have this energy. This is just the energy corresponding to the state in the Hamiltonian that ensures actually the normalization. And if you would just look at that here and take the derivative, you would end up here. Now, I applied this here to the problem we had at the beginning. If you start again in the equal superposition state that has overlap with all possible solutions, and you apply imaginary time evolution, you quickly go down to the optimal solution, which had value -2. And here, this is the plot of the amplitudes at time 0, 0.25, and 1. You see you start in the equal superposition state, then it puts emphasis on the larger, on the smaller eigenvalues, on the better solutions. Already here, you have a strong emphasis on the optimal solution, and at 1, you're already almost at the best solution. So imaginary time evolution is a really nice algorithm. The problem is it's a non-unitary evolution. That makes it pretty hard to implement on a quantum computer. So it's a very nice idea, but not so easy to actually apply. And this is not really surprising, because with that you can prepare Gibbs states, you can prepare ground states, and so on. So those are QMA hard problems. So if it would be too easy, then something would be wrong here. But there are nice ways to approximate it. One is variational quantum imaginary time evolution, or Wahrheit. what we do here is we take a parameterized circuit, an ansatz, can be pretty arbitrary, so psi theta, and we use McLachlan's variational principle to project the state dynamics that's given by the differential equation to the parameters. And I don't go through all the details here. You can read that up in the paper. But the rationale is really to project what you would like to do in the state space to the best you can do in the parameter space or in the manifold in the exponential Hilbert space. And this leads you to a differential equation for your parameters. So then you can really evolve the parameters, and you move through your parameterized state or parameterized space here, and you approximate the imaginary time evolution with that. Now here it's just theta dot, so the time derivative of theta is given by this inverse matrix and this vector, and they are given by the, or proportional to the quantum Fisher information matrix and the energy gradient of your state. These are things you can evaluate on a quantum computer, and then you can evaluate this time derivative of your parameters. Then you can apply your favorite ODE solver. Easiest one is just forward Euler to try to follow these parameters. All right. This is, some people here, I'm quite sure, are familiar with quantum natural gradients. This is very, very much related to quantum natural gradients, and it actually coincides in some cases. And what you do here in a way is, instead of just minimizing the energy with respect to your parameters, you're going from the quantum Fisher information in a way translates from your parameter geometry and your Hilbert space geometry. So it kind of relates the two. Like, how much does your state actually change if you change your parameter? This you'd like to understand, and this is the link to the natural gradients. The problem with this is that this quantum Fisher information matrix, I wrote down the formula here. You can evaluate this by evaluating 3 circuits that correspond to this inner products here. And since it's a matrix, with respect to your parameters, you have to do 3 circuits for every pair of parameters. So it scales quadratically in the number of parameters of your ansatz. And this is pretty expensive. So this is getting quite quickly a problem if you have large ansatz with hundreds of parameters. And the question now is, how can we speed this up? And before I go into how we can do this for Wahrheit, I want to quickly introduce another concept. This is SPSA, or simultaneous perturbation stochastic approximation. That's an optimization algorithm for noisy optimization. You might have heard about that. It's quite popular for VQE and optimizing parameterized quantum circuits. The idea is very simple. So you have some function. Here it's 2 parameters. Then you draw a random direction, where for each component you just take a Bernoulli variable and plus minus 1. And then what you do is you evaluate your function doing a small step in this direction in one direction, other direction, but in this direction, not like in standard finite difference along your coordinate axis, but in a random direction. And then you use this So I think it's an easy to use package to start with an optimization problem and try these different quantum optimization algorithms. And this QAOA runtime actually is also exposed such that you can plug it in here into this minimum eigensolver and then use it within this package. All right, now with that, I'm already coming to the last slide. So I think quantum optimization it's a very active area of research. And I think if we find an advantage, if we find something that works, that finds applicability in so many domains. So I think this is that the usefulness of a quantum advantage in optimization is huge if we can realize that. However, to date, it's really not that clear yet. We have some heuristics, we have some ideas, but there's no end-to-end, let's say some proposal for a clear quantum advantage. Like there are things like Grover, which at some point at large scales might make a difference, but I think near term, there's still a lot of things not known. We have very good proposals, and I think the hardware now reaches really a scale, a quality, and a speed that we can really try this on interesting problem instances. And like if we now get to like the 100 qubits and so on, this is where we have first maybe academic problem instances that are difficult classically. So this is where we really can study this, understand the performance better, and reach interesting scales. I mentioned speed. Peter mentioned speed earlier as well. We saw this runtime for QAOA, where even if you do not do any optimization, you're already like at 1 minute for 500 variables. I think speed will be also crucial for these algorithms. If you think that like this is on superconducting hardware, if you go to other hardware which is orders of magnitude slower, then running these algorithms at scale will become prohibitive at some point. Now, I think one of the key open questions is whether we find good ways for certain problems to define good variational ansatz, good circuits that we can use in algorithms like natural SPSA to get good performance. Because in general, we know we cannot get a big advantage. Like, it won't be a solution for all problems. So we need to find ways to build circuits based on problems. QAOA is one example, where you take an operator and derive your circuit. But maybe we find different rules or approaches like that for things like quantum natural SPSA as well. So these are a research direction that I think is important. I mentioned 3 kind of algorithmic primitives, and not all others. You might have seen some recent papers about quantum-enhanced Markov chain Monte Carlo, which can lead to some I think polynomial speedups. There are proposals around counter-diabatic annealing. What this means is you have your annealing setting, but that you add additional terms to your Hamiltonian, to a mixer Hamiltonian, that kind of suppress this jump to excited state, so you can anneal faster. In general, you don't know which other terms to put there, but there's some interesting. And then, as I mentioned, going beyond binary to mixed integer and also a very interesting domain for the time being. Like from a research perspective, it often boils down to getting the all right, so with that, thank you for lunch, and I also thank my collaborators here at EPFL. Some of this work was done with and collaborators at ETH, and of course my colleagues at IBM, which
Thanks a lot.
and I think we have plenty of time for questions.
Yes, we have a little. This is a little present.
Thank you very much.
So if anyone has questions. Yeah.
Okay, thank you. It was a great talk. So I was always wondering, can one show that the QAOA is better than just classical simulated annealing? At least, you know, if you go to say big systems like a big number of spins, the simulated annealing, classical simulated annealing gives you only a single string. So you not necessarily converge to the ground state, but you can converge to something decent. On the other hand, QAOA can have this problem of exponentially small overlap with the ground state, and then even if you have a trained circuit, you try to sample the strings, and it's very unlikely that you will get the ground state through sample. What is the theoretical, like, can you prove, at least in some cases, that quantum computing can actually bring something in this area?
I mean, what has been proved so far is that if you go beyond the threshold, you're sure that it won't give you. So there's like the no presented. At depth, if I remember. Of qubits that we can also just I think the best you can really do is demonstrate.
Okay, so okay.
I just had a thought which is maybe not super related to the talk itself, but you presented algorithms for solving.
I mean, candidate solutions, we usually are talking unconstrained problems. Constrained problems, then you just need to satisfy. Yes. And so on, and try to find lower bounds to the optimal. This is classical. I'm not familiar of any quantum approach here, but you could, of course, mix things. You can search for good candidates with a quantum computer and this is mostly class.
Maybe I lost the condition, but for the imaginary time of do we need the Hamiltonian to be diagonal too?
In general, not, no.
Yeah, right.
You can